Okay, let's begin Chapter 4 by scrolling ahead to the end of the note packet and looking at the goals of our Chapter 4 studies. So we're doing a little bit of work in the beginning on looking at some mystery of matter videos, just to be familiar with the history of how people know about the parts of an atom. So Chapter 4, we're going to look at the periodic table, protons, neutrons, electrons, isotopes, and all of these things are super tiny. How do we know what they even are? And it's an interesting story, so we're going to start trying to just be familiar with the basics of that. All right, and then after we know how they were discovered, we should be familiar with what the atomic particles are: proton, neutron, and electron, what their mass is, what their charge is, which ones are in the nucleus. And we should also be familiar with how an isotope is written so that we can figure out the number of protons, neutrons, and electrons in the isotope of a particular element. And then we should also know what the average atomic mass means. The periodic table has an atomic mass, and so we should be able to calculate the atomic mass from the different isotopes that we have. Also, if elements have a different number of protons and electrons, we should be able to figure out the charge. So then we are going to take a look at the periodic table and identify where the metals are, the nonmetals, the metalloids, and also any special groups or families of elements. So just a little familiarity with the periodic table. And then we are going to take a look at electron configurations. So these are a little bit unusual if you've never seen them before. I have a few different videos, myself doing some, and I also found some YouTubers who are taking a look at the electron configuration, which orbitals the electrons are located in. Once we've looked at the electron configuration, we can make sense of the different columns on the periodic table, why some of them have a predictable charge, an ion that forms with a certain kind of charge on it. And that has to do with how many valence electrons each element has. The number of valence electrons it has is connected to the predictable charge that an element is likely to get when it forms an ion. And then we'll also look at some trends in the periodic table, the size of different elements, their ionization energies, metallic characters. And also, this is going to be important for the next module as well. We're going to be naming some compounds in the next module, but we have to start out with knowing the names of some of the more common elements that we're going to be using. So I have a Quizlet posted about that. Okay, so how did we figure out what matter is made of? We already mentioned Antoine Lavoisier and his work on the conservation of matter, that whenever you changed one type of matter into another with a chemical transformation, the amount that you had would stay constant. Then it was further noted that if you have a pure substance and you analyzed what elements it's made of by mass, then that ratio is always going to be the same. So sodium chloride would always have the same amount of sodium and chloride by mass. A mass of the sodium wouldn't equal the mass of the chloride, but it would be the same ratio in every pure sample of sodium chloride that you came up with. And then a little bit later on, it was also noted that sometimes there are two different compounds that can form from two elements. Like, for example, copper and chloride can form two different types of compounds. And so the ratio of copper and chloride is not always the same in all copper chloride compounds, but there's two types, and within that type, the ratios are going to be either one or the other. And the two ratios that exist for copper and chloride are small multiples of each other. So the ratio of chlorine to copper by mass in this type of copper chloride is twice the ratio of what the chloride copper masses are in this other type of copper chloride compound. So it seemed that elements were always following these patterns, always having fairly simple combinations with each other. And from this information came a theory by John Dalton. Since it seemed like the amounts of elements were fairly fixed, John Dalton came up with a model that would try to explain all these observations. And this atomic theory was that matter was all composed of atoms, atoms that cannot be broken down any smaller. So atom meaning unable to cut. So you can't cut anything smaller than an atom. So the elements are pure in that they only have one type of atom. And each element has a different kind of atom from other elements. Like all atoms of carbon are the same, and they're all different from atoms of oxygen or atoms of chlorine. Compounds come into existence when you combine two or more elements, and they are combined in small whole number ratios. So what today we illustrate with a chemical formula, like for example, we know that copper 2 chloride has 2 chlorines for every 1 copper, and copper 1 chloride has 1 chlorine for every 1 copper. So these ratios, a 1:2 ratio and a 1:1 ratio, these simple small number ratios are the way that different elements combine to make compounds. And then when you do a chemical change, these atoms themselves don't change. They just rearrange and become different compounds. So this particular reaction that I've drawn has atoms of hydrogen and atoms of oxygen. And so these atoms don't change. We have hydrogen and oxygen together as hydrogen peroxide at the beginning. Then we do have a change in that there's no hydrogen peroxide at the end. There's water and oxygen, but the oxygen atoms did not change and the hydrogen atoms did not change. They just changed in how many were connected to each other. The ratios changed a little bit. Instead of 2 hydrogens for every 2 in hydrogen peroxide, we now have 2 hydrogens for every 1 oxygen in water, and then we also have some additional oxygen as gaseous oxygen molecules. Dalton did not know about the parts of the atom. To him, the atom was the smallest unit of matter that exists, and it's still true that an atom of an element is the smallest piece of that element that is still that element. But there are smaller pieces within atoms. The discovery of electrons, as people studied electricity more and more, we learned that electrons were negatively charged particles. Even the charge to mass ratio on electrons was worked out, and the mass of an electron. And then we saw in the videos the work of Rutherford and the discovery of the nucleus. And that is where the positive charges are concentrated in the small nucleus, with the electrons in a cloud outside of the nucleus. A little bit later than that was the discovery that even the same element could have slightly different masses. So this is a deviation from what Dalton was aware of. So Dalton thought that 2 atoms of the same element would always be completely the same, and we know that 2 atoms of the same element can have a slightly different mass, and that is because of neutrons, which affect the mass of the isotope but not the charge or the chemical properties. So it was very difficult to discover these different isotopes because the only thing that's different is the mass, and that only very slightly. So the chemical properties are the same, and the charge in the nucleus is the same, but the mass is slightly different. The answers to these are in the answer key, so I will skip going over these in the video just to make sure that people can take a look at it on their own. All right, so after all this scientific work, we came up with these 3 subatomic particles: electrons, protons, and neutrons. The protons and the neutrons are together in the nucleus, and that's where almost all of the mass of the atom is. So there's 1 atomic mass unit, close to 1 atomic mass unit per proton, and close to 1 atomic mass unit per neutron, whereas the electron has way, way less than 1 atomic mass unit as its mass. And so we don't usually count electrons towards the mass of an element, because we would have to have 2,000 of them to equal the mass of one proton, and there are no elements that have nearly that amount. So effectively, we count the electron as not having mass, even though it does have a small mass, and the proton and the neutron as being about 1 each. And then we have charges on electrons and protons, but not on neutrons. Neutrons are neutral, they have 0 charge, and protons have a positive 1 charge, and electrons have a negative 1 charge. The protons, as we see in some of those Mystery of Matter videos about Moseley's work, the protons are what determine the element's identity. So for example, carbon has 6 protons. The atomic number for carbon is 6, and so any atom that has 6 protons is an atom of carbon. And all atoms of carbon have 6 protons. If there's something other than 6 protons, then that is an atom, but it's not carbon. It's not a carbon atom. So when we want to write an isotope or an element to show all the particles that it has, we would use the elemental symbol. So for example, for carbon, the elemental symbol is C. So we're going to try to show carbon, the type of carbon atom that has 6 protons, 6 neutrons, and 6 electrons. So that's the type that we're going to show here in this isotope. But it has 6 protons. That is the atomic number that goes to the left as a subscript. If the carbon has 6 neutrons, then A would equal 6 plus 6, which is 12. So that would be carbon 12. Atomic number has to equal the number of protons. The mass number, the superscript to the left, has to equal the sum of the protons and the neutrons. So that would be 12. And the charge, I just put a little asterisk here to show the charge. That would be the number of protons minus the number of electrons, because there's a negative charge for each electron. So this particular carbon has a 0 charge. We don't have to write that. You can if you want to, but if it's 0 charge, we don't have to write the charge there. So if you don't see a charge written, we know that the charge is 0. That's what it says over here. So on the next page, we have an example of isotopes, which are the same element because they have the same number of protons. Magnesium has 12 protons, otherwise it wouldn't be magnesium. But the mass number is different, and that is because there's a different number of neutrons. So let's figure out for each of these how many protons, neutrons, and electrons it has. We'll do that one in green. We'll do this one in blue. All right, so the proton is easy because the number of protons equals the atomic number. So whatever number you see written here, that's the number of protons. This one has 12, and this one also has 12. For this green one, the A, the mass number, is written as 24. That has 24 mass. And we know that that is the number of protons plus the number of neutrons. So the number A, the mass number, minus the number of protons would equal the number of neutrons. So we just subtracted P from both sides of the equation here, and we got neutrons alone on the right, A minus P on the left. So our mass number is 24, our number of protons is 12, and that gives 12 as the number of neutrons in this isotope. So when we take the mass number and subtract the protons for this isotope on the left, we get 25 minus 12. So our number of neutrons in this is 13, which gives us a higher mass. We have more neutrons. So since our charge is our protons minus electrons, then if we add the electrons to each side, we get the electrons plus the charge being equal to the protons. Then if we subtract the charge from each side, we can find the number of electrons by taking the number of protons and subtracting the charge. So here we don't have a charge written, so we know that the charge is 0. So for this green isotope, we take the protons, which is 12, we subtract the charge, which is 0, and we get 12 as our number of electrons. And that makes sense because if the number of protons and electrons are the same, they balance each other and the charge overall will be 0. And we do the same thing on this side, 12 protons minus a charge of 0. The protons minus the charge is our electrons, which on this side is also 12. So these two isotopes have the same number of protons, the same number of electrons, and they differ in the number of neutrons. So that's the only thing that's different about these two isotopes. Okay, so again, we have some comprehension questions to make sure that you've been paying attention to the properties that different particles have, their locations, their mass, and their charge. And so hopefully you guys can fill those out and check on the answer key for that. All right, so let's make sure that we can look at the way an isotope is written and be able to figure out how many protons, neutrons, and electrons it has. So remember, for the protons, that is just the atomic number, which is written in the lower left-hand corner, the subscript to the left. So we have 8 protons here. This particular isotope would have 6. This one would have 26. We have 17 here. And if we are going to write an isotope with 11 protons, we would write that as a subscript to the left. To figure out the neutrons, we need to take the mass number and subtract the protons that we have. So 17 mass minus 8 of those mass being protons leaves 9 neutrons. So for this one, we have a mass of 14 minus the 6 protons would give us 8 neutrons. For this one, we have 56 total mass minus 26 of that being protons, and so we have 30 neutrons. And for this one, we have 37 mass minus 17 protons, so 20 neutrons. If we know that we have 12 neutrons and 11 protons, then for this one, the mass number is going to be the sum of those, or 23. So this will have a mass number of 23. The number of electrons can be found by taking the number of protons and subtracting the charge, whatever kind of charge we have. So here we have 8 protons and we are subtracting a -2 charge, and that is how we came up with 10 electrons. So if we have 10 negative charges and only 8 positive charges, overall we are going to have a charge of -2. Here we have 6 protons and a charge of 0. So we have 6 electrons in this isotope. Here we have 26 protons and we are subtracting a +2 charge. So that would be 24 electrons. We have fewer electrons than we do protons. That's why the charge is positive. Here we have 17 protons and we are subtracting a -1 charge. So we have 18 electrons. So more electrons than protons will give us a negative charge. Fewer electrons than protons will give us a positive charge. So to figure out the charge, it's the number of protons minus electrons. So for this unknown isotope, we have 11 protons minus 10 electrons, so we have a +1 charge on this isotope. Now to find out the identity, we have to look up on the periodic table and see which element has an atomic number of 11, which would be sodium. Na is number 11 on our periodic table. Besides the practice problems, if you want to have a little bit more practice with isotopes, you can go in Module 3 to this Fun with Isotopes page. I have a link to some simulators here. This first one has to do with isotopes. The second one has to do with the average atomic mass, section 4.7. We have a discussion about this particular simulator, so you'll have to check that out. And then we also have a link to a periodic table that shows the different abundance of isotopes that exist for each element. These are some good hands-on simulations to help you learn the material. I suggest trying this one because it has the symbol that we were just talking about. You can put in some protons and some neutrons. The charge and the mass number and the atomic number all change depending on how many particles you put in here. It keeps a tally over here of how many protons, neutrons, and electrons there are. You can also have it show if it's stable or unstable. If you add too many neutrons, you can make it unstable if the mass is too high. So if you need some help understanding the charge and the mass and the atomic number, you can try this simulator.